Hello and welcome back to the course on artificial intelligence. And today we're talking about Markov decision processes, or MDPs. Let's have a look what we've got today. So last time we stopped on the concept of a map. So because we've calculated the values based on the Bellman equation, we can derive this map for our agent of this maze. And basically what that means is wherever the agent starts, so let's say it starts over there, it knows exactly which steps to take in order to get to the finish line. So it just goes up, up, right, and done. And so the question here is that it? Is it really that simple? Is reinforcement learning really that, for the lack of a better word, boring? Once you have the map, that's it. All you have to do is you're done. You just follow the map. Well, the reality is that it's not actually that all simple. And that's a good thing because it makes this course more interesting for us and we can actually solve much more complex problems. So this is where Markov processes come in. But first, we're going to talk about two things. We're going to talk about deterministic search versus non-deterministic search. So let's talk about the concept of deterministic search. This is our agent in the maze, and deterministic search means that if the agent decides to go up, then what will happen is, with 100% probability, it will go up. That's exactly what will happen. There's no other options. Once it says go up or clicks the up arrow, it will go up. There's no other options. Now, on the other hand, non-deterministic search is when our agent says it wants to go up. There are actually a couple of options. For example, there could be 3 options. And we're going to be looking at an example where there are 3 options, but it doesn't have to be limited to 3. It could be 4. It could be, different. Depends on the problem. The randomness could be different, but in our case, there could be 3 options. With an 80% chance, he does go up. But then with a 10% chance, when he wants to go up, he'll actually go to the left, just because that's how the environment works. That's the world that he lives in. And with another 10% chance, he'll actually go right. And in this case, he'll fall into the fire pit. So that is how it all works. That's an example of a non-deterministic search, a stochastic process. And what the point of this is to make a more realistic model of what could actually happen in a real world, in a real world type of problem. Because very rarely do you get situations like this when you do something and it happens exactly that way. And even if you think about it in terms of games, let's say you've got an agent playing Pac-Man, well, not always is it the case that if he's standing in this square, he goes up, he will get the same exact result every time. He will indeed go up, but maybe in one case he won't get eaten by a ghost, in another case he will get eaten by a ghost. So as you can see, there's some randomness to it because it depends on how the ghosts are moving, and they don't always move the same way. They don't always start in the same locations. So it's very logical, it's fair that there is some randomness. There's something that is not under the control of the agent. And this is just a way for us to represent that in order for us to learn how we can deal with it and how that affects the Bellman equation, how it affects the whole reinforcement learning process. But at the same time, the randomness is of course not limited to if you go up, there's a 10% chance you'll go right, or 10% chance you'll go left. Or if you go down, there's a 10% chance you'll go right or left, or if you go right, there's a 10% chance you'll go up or down. It's not limited to where you're going to end up. Sometimes you might have a problem that is exactly like this. Sometimes the probabilities might be different. Sometimes the randomness might boil down to something else. It might be boiled down, like in that example of Pac-Man, of the ghosts eating you or not eating you, or it might boil down to something different. For instance, like there's like if the agent is playing Doom, and then there's something like a monster which is going to shoot him in one case, another case there's a probability with which it will get shot and with which it won't get shot, and so on. So something that is out of the control of the agent, something that it cannot predict. That's what we're modeling here in non-deterministic search. And this is where we have directly approached 2 new concepts: Markov processes a Markov process and a Markov decision process. So let's have a look at these. And you know how much I don't like to put definitions and lots of text on the slides, but in this case, it is necessary for us to go through them. So let's have a look. A stochastic process has a Markov property if the conditional probability distribution of future states of the process, conditional on both past and present states, depends only upon the present state, not on the sequence of events that preceded it. A process with this property is called a Markov process. Very complex definition, and it kind of like even a little bit, not contradicts itself, but it feels like it contradicts itself. So here it says conditional both for past and the present states, depends only upon, but at the same time, it only depends upon the present state. So don't get too bogged down in that. I'll break it down in simple terms. So a Markov property is when your future states, so not just your choice, but the whole thing, your choice and the environment, it will only, like the results of the action you take in that environment will only depend on where you are now. It will not depend on how you got there. And that's it. So that's a Markov property, and a process which has this property is called a Markov process. So to put it into an example, so if your agent is here, and if he decides to go up, he might go, in our case, in our non-deterministic search example, he actually might go left and right, or right. That's because we have that stochasticity inside our environment. We have that randomness inside our environment. So any one of these three might happen. But the key here is that this is a Markov process because we don't care how he got here. He could have come from the top, ended up here. He could have come from the left, ended up here. He could have come from the bottom, ended up here. He could have moved around here like 100,000 times and then got here. It does not matter what happened before. Only what matters is which state is he in now. And so the probabilities of going left or right or up, they will always be the same if he's in this state now. And so that's basically just saying, it doesn't matter what happened before, we're here now, this is the state you're in. And don't forget that state doesn't just mean where he's standing. The state is the state of the agent in the environment. So is there like monsters on the right, or are there monsters on the left, or is the ghost coming from the top or the bottom? Whatever state you're in now, doesn't matter how you got there, doesn't matter how it all came to be that you're there in that state now. What will happen in the future is only determined by the state you're in now, plus the actions you will take. Then plus, of course, the randomness that is overlaid on top of that. So that's a Markov process. And a Markov decision process, or an MDP, or Markov decision processes, provide a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under control of a decision maker. So important to understand that Markov decision processes are different. A different whole concept to a Markov process. They're kind of like a mathematical framework. So, but at the same time, I thought it was important for us to understand what a Markov process is, because I think it still helps in understanding of a Markov decision process. So, a Markov decision process is exactly what we've been discussing up till now. So that the agent lives in this environment where it has control. Like, remember previously it had full control of what's going on, but now it has a little bit less control. It can decide to go up, but it actually knows, okay, so if I go up, there's an 80% chance I'll go up, there's a 10% chance I'll go left, 10% chance I'll go right. So not everything is fully under its control. There is some randomness in this environment. And that's exactly what a Markov decision process is. A Markov decision process is the framework that the agent will use in order to understand what to do in this environment. So we've got an environment with some stochasticity, some randomness, and now the agent has to choose, for instance, should it go up, down, left, or right. It has to make that decision. It doesn't know what to do. And in order to make that decision, it's going to apply a framework. It's going to be using a Markov decision process in order to make that decision, what's going to happen, where it's going to go. And so basically this environment that poses this problem, it is referred to the Markov decision process. So it's the framework that agent using. At the same time, the environment is referred to that the agent is operating in a Markov decision process environment. And so basically here we've got two concepts. We've got the Markov process is the way this environment is designed, that what happens from where you are now doesn't depend on the past. And at the same time, we've got the Markov decision process is the framework that the agent is going to be using in order to solve this environment. And the good news is that the Markov decision process, or that framework that we're talking about, is actually just an add-on to our Bellman equation. It is the Bellman equation, but just a bit more sophisticated. So let's have a look at that. This is our Bellman equation so far. It's the maximum of all possible actions. So the value of being in a state is the maximum of all possible actions that you can take from that state. The maximum is taken from the reward that you would get by taking that action in that state, plus a discount factor times the value of the next state, which is S prime. So that's what we've had so far. And now, because we have some randomness in our whole process, this part will change, because we don't actually know which state we'll end up in. We don't know what S prime will be. Will it be If we're going up, will it be up, or will it be left, or will it be right? So we actually have to place this with the expected value of the next state. So here we're going to replace this. So there's 3 possible states we can end up in. And so we're going to replace that with that's a value. That state has a value of S1 prime. That state has a V of S prime 2, S2 prime. And this state has a value of V of S3 prime. So now we're going to multiply the state that we actually are intending to go into by 80%, because that's our probability of getting into that state, plus the probability of getting into this state, 10% plus probability of getting in this state. So this is just our expected value. So if from statistics, if we take the expected value of getting into of the state that we'll get into, so kind of like the average. What's the average of what we'll get? And then we replace that over here. Then we get this equation. Now, it jumps very quickly just because this equation is bigger, but if you look at it carefully, you'll see it's exactly the same thing. So you've got max here, you've got max here. Then you've got R of S and A, you've got R of S and A. Here you've got gamma, you've got gamma. And then finally, here you've got V. So you knew exactly it was a deterministic search. You knew which state you'll get into. Now you don't know which state you'll get into. So instead of taking V, you're taking the expected value of the state you'll get into, or of the future state, or just in simpler terms, you're just taking the average of what you'll get into. So, if like it was like if it was a 33% chance, then it'll be like this plus this plus this divided by 3, basically. But in this case, it's not exactly like average. It's a weighted average because of your probabilities here. So here you've got the probability of when you're in this state, you take this action of getting into state S prime times the value of S prime and summed across all S primes that you could possibly get into over here. So exactly what we had 3 here, 1, 2, 3, add them up, multiply by probabilities, add them up. Same here, 1, 2, 3, multiply them by probabilities and add them up. And that is your new Bellman equation. Congratulations. This is what we're going to be working with going forward. And that is the framework that is used in Markov decision processes. So that is the framework that solves this, that agents use to solve this whole stochastic, non-deterministic search problem where there's random events that are happening that they cannot control. So it's much more complex, but as you can see, because we built up slowly to it, now we already know about this, we already know about this, we already know about this. We know about this, we know about this. So all we did is we just introduced this part over here because there are probabilities involved in the action or the consequences of your action are non-deterministic. They are based on certain probabilities. And so there we go. That's how a Markov decision process works and the underlying equation behind it. Once again, it is something that is more closely resembles real-world problems, real-world scenarios, or even game scenarios, because not everything is straightforward. There is some randomness involved, and not always will taking an action in a certain state not always will it lead to the same outcome. And so this is what we're going to be dealing with going forward, and that's going to make things way more interesting. So hopefully you're excited for that and excited to see what's going to come next. And in the meantime, I found a really cool paper for you to have a look at. This time it's a very applied paper. So this one's actually really interesting to read through. It's called A Survey of Applications of Markov Decision Processes, and it was written by White in 1993. There's a link, and it'll show you examples of where Markov decision processes actually are used to model real life scenarios. I was very excited by this. I was impressed by some examples. So population harvesting, for instance. So let's say you have some fish and you know what the population of the fish is. You need to decide how many fish can we fish out this year, and so that's your current state. That's the action that you're taking. How many can we fish out this year? So that what are the possible outcomes of that? How many fish will we have next year? How many fish will we have the year after and the year after and so on? And it's not deterministic because it's not like if you take out, 90% of the population, then next year you will have, back to 100%. It's not exactly deterministic. There are certain random factors involved which are out of our control, and therefore we have to understand what's going to happen. We have to model what's going to happen. That's where a Markov decision process is used. Agriculture, there's an example like same thing like harvesting crops. How much crops do we harvest? How much do we not harvest? Another one which I looked at, finance and investment. Like an insurance company needs to decide how much of its funds it will invest in any given, I think, day or year or some period of time. And there are certain factors that are out of its control. For instance, the market movements, it doesn't know what can happen. So it needs to actually model that somehow, and a Markov decision process is used for that. So here you can see lots and lots of examples, and this is the number of examples given, I think, for each one. And so, even sports, 2 examples for sports and epidemics and motor insurance claims, inspections and maintenance and repair and so on. So very interesting. Have a look at that just to give you an understanding of, hey, this is not just all made up stuff, hypothetical, the Matrix type of thing. This is actually a real world scenario. So it'll give you a better understanding. And this is what we talked about in the promotional video for this course, that or the description of the course, that we're going to inspire you and your intuition to give you ideas for how to use AI in real life. This is your opportunity. Look at this paper to understand, okay, so we're going to be dealing with Markov decision processes going forward. That's really cool. What do they look like in real life? And this possibly could trigger some ideas for you how you could apply AI in the future to make the world a better place. And we'd be super happy about that. We'd be super happy if you could use what you learn in this course to make the world a better place with AI. How fantastic would that be? Now make sure to check out these videos on the right or the full course in the description to continue your learning. And I look forward to seeing you there.